Hello, everyone. Let's start with today's lecture, which is on intelligent exploration. We had started discussing about this in last week on Wednesday. We said that, to be able to act in the world, you need to exploit what you know and explore so that you get to know more about the world in case you can use this extra knowledge to act better in the future. We said that epsilon greedy is not a good idea for exploration because it doesn't model what it doesn't know. It just explores randomly by adding random noise on actions. There's nothing intelligent about that. So the question is, how can we do intelligent exploration? Then we jumped and started discussing about intrinsic motivation. What motivates humans to just explore around? We said that these are some different forces, different than satisfying hunger or warmth and so on and so forth. We said it is the let's say, curiosity to see how you can actuate your environment. How can you to explore the affordances of your environment? And we said that such curiosity is different than the survival instinct, all right? Another thing we said is that if we figure out how to make mathematical formulations of those intrinsic curiosities, then we don't need to worry about coding up external rewards for different tasks, which is a difficult process in the first place, because we'll be able to have our agents explore most of the things independently, on their own, autonomously, okay? So that's what we said. This was our introduction. And where we stopped is on specific mathematical formulations of this curiosity, okay? The first thing we said is that, we'll be using ensembles of Q functions. Ensembles on Q functions will simply be used to model our uncertainty. They're inspired from Thompson sampling, as I'm going to show in a second. The second thing we're going to see is state counting. How many times we've been in a particular state. We know that we cannot enumerate states in the continuous world, but we'll do some discretizations, all right? So we'll featureize them, we'll jump to a latent feature space and we'll bin in that space using hashing and see, we'll be counting essentially how many times I've been to a particular bin. Okay, and I will give high reward if I land on a bin that I haven't been before, or I have been little times before. And then we'll talk about the model prediction error, which means that we'll be learning a model of the world and reward the agent when it makes mistakes, when it actually acts in a way that the model cannot predict its transitions. There is something weird in this formulation, but we will visit it in detail. Okay, and the last two works that are extremely, extremely important. Again, we will be forming a model of the world, but instead of that model of the world being parametric, some neural function that takes you from state and action to next state is going to be a non-parametric. It's going to be a graph of nodes and edges that we'll be building as we move around, and we'll be using this non-parametric model of the world to explore intelligent and search for maximizing our rewards, and we'll see the extreme, huge capabilities that such an external non-parametric model can give in simulation environments. Okay, so this is the plan for today's lecture. Any questions? Okay.
Why specifically simulation environments?
It's not specific simulation, simply because the whole RL is landed simulation environments. However, you will see when we talk about our sim to real lecture, which is probably super soon. Okay, I'll talk to you there about what are the big successes on real robots that have actually, stem from reinforcement learning, right? So one big success that I can think of that we've seen so far is transporter networks, but this had zero reinforcement learning. It was all imitation learning. Okay, so in that lecture, you'll see that there are works that are able to use reinforcement learning in simulation with extreme domain randomization to actually learn robots and behaviors in the real world. Okay, all right, that's the only reason. But all these ideas today, you'll be able to use them no matter where you are. Okay, yes.
How are you able to represent complex environments with non-parametric graphs? How are you able to do?
Well, yes. So we will visit that two bullets, but the idea is that you visit a particular state, okay, and then you go to another state and you put in your graph the state, the features, and an edge of which state landed you to another state. That's it. So that's one way to do it. Okay.
That entails being able to explore all the states in the environment to create that graph.
Exactly, yes. So, and each time you land in a new state, then you search in your memory. Have I been there before? You're like, oh, here is the room with that, let's say, pink portrait. Oh, yes, I visited that part of the museum. Let me go to a different room, okay? So you just match the new state features with this non-parametric memory repo that you built to figure out, am I in a new state or not? As simple as that, okay? Because what we care here to capture is novelty of states and novelty of transitions, okay? Other questions? All right, so let's just jump. We'll go slowly, okay? In terms of excitement, like the excitement is going to be towards the end of the lecture, it's going to go up and up and up, okay? So we'll start kind of normally with, okay, ensembles of Q functions. Okay, nothing special about this. So let me remind you about Thompson sampling. So what was in Thompson sampling? We said, same that for UCB, that if you really want to take good decisions when you in bandits problem, okay, non-sequential setups, you really need to capture uncertainty. And one way we, propose to capture such uncertainty is to keep a distribution of those mean rewards of the different arms, not to have a point estimate, not one mean estimate, but rather a distribution. And then when we're ready to act, okay, then we will sample from that distribution. The good idea here is that if your distribution is close to uniform, which is wide, fat, and short, right, means like you explore a lot, you have high uncertainty. So look at if you're the red distribution, and then you sample from the red, you have a chance to be the winning arm, okay? Now, if you're tall and thin, then this means that you have low uncertainty, so all the samples probably will be concentrated around, the high probability regime of the mean reward values. So in this way, if you model the quantities you care about as distributions, then you can approach this exploration in this very nice and uniform way, where we just sample from our distributions and we follow the argmax. No need to add epsilon noise, nothing of that sort, okay? And then just play the arm. Based on what you see, you go, you update the distributions, and so on and so forth. And the most obvious question here is that this is for multi-arm bandits, which means the stateless setup where I just take one action and I see the reward. What about sequential setups? Okay, where I need to act multiple times and the reward will come later in the future and so on and so forth. What would be the analogous thing of modeling your uncertainty and having a distribution over, let's say, the action values? Okay, if you remember the mean reward, we call it in the first lecture Q, which was the action value. So the action values in the general case are the Q functions, guys. Okay, it's not something that you feed it the action and get the number. It's something that you feed a state in an action because it depends. Different actions are good in different states, and it tells you how good or bad it is on expectation. All right, so Q is the analogous of the small q that we saw in the first lecture. So what we will try to do, instead of having one point estimate for our Q function, instead of having one neural network represented it, we want to have a distribution over functions. And because distributions over functions, I mean, we discussed about this before, if you remember. Ideally, we want to represent a distribution over those Q functions instead of a single point estimate. And then what we will do, we'll just sample from that distribution, okay? And we'll just follow. We'll just, act as argmax with respect to the Q that we just sampled without adding any epsilon noise. While when you were using a single Q, right, for deep Q learning, for example, you had to add noise to be able to explore. Now you don't need to anymore because you represent distribution over Q functions. Is this clear? Yes?
Is this distribution parameterized by a theta function?
Yeah, we don't know so far how. This is very difficult to do. You have a whole neural network. But if you remember, we had discussed about this. I'll tell you. But let's assume we can do that. If we could do that, then this is what the procedure that we would follow, right? Then we will collect a new trajectory, we see its rewards, we'll update our Q distribution or our Q function, sample again, and so on and so forth. No need for epsilon greedy, so this is great. But then we go back to the question of your colleague. How are we going to represent that distribution over neural networks? Okay. The first thing is to use Bayesian neural networks. Does anybody want to remind us what we've mentioned this in the course before? What is a Bayesian neural network? A distribution. Every weight of the network is sampled from a distribution. all right? And specifically, the distributions that I've seen in papers is, for example, two model Gaussian distributions, okay? So you don't have one point estimate for each weight and bias, you just have a small distribution and you sample those hundreds of thousands of distributions if you have hundreds of thousands of parameters, and that's how you generate instantiations of neural networks. So you sample from them and here you have different networks. So we have seen that, but to be honest, this is a little bit painful to train, okay? And we've discussed in the past that actually, do you remember when this came up before? In PETs, when we wanted the distribution over dynamics models. And we said, okay, forget about Bayesian neural networks, we will just have ensembles. And this is a good approximation. We will have multiple neural networks with different initializations trained on different subsets of the data. And our hope that all the components of the ensemble would agree on things they know, and they all will fail, predict different things when they don't know outside of the training distribution. Okay, that's what's the idea. That's totally great. Now, instead of having completely disjoint neural networks, you can have something that looks like this, which is a shared backbone and different heads. And in this way, the backbone shares training data, but the different heads, they're trained on different subsets of the data. Okay, that's nice. Yeah, let's forget that the dropout is not a good approximation, so let's forget about that. Okay, so let's see. In fact, that was a paper, 2016, deep exploration with bootstrapped DQN, okay, of Osband et al., where this is precisely what they did. They had a distribution over Q functions captured with an ensemble, and then they would sample from that set of the ensemble. At each time, they would sample one of those networks, and then would follow that network for the whole trajectory. And then next time, they would sample from another model of the ensemble, and so on and so forth. Okay. Yeah. So different Q values have high entropy and things they don't know, and we have low entropy when they know, and so on. So that's it, guys. So basically, you don't need now to add epsilon greedy, because by sampling different Q functions, essentially they guide you in different parts of the space. One Q function will say, oh, yeah, this way is good. This way, it's not good because look, I hit the table, but that Q function didn't know about that. And then it guides you to go straight there. Now, on the parts of the training space where they all know, on the state and action space where they all know, they all give you similar ideas, okay? Similar guidance of what actions to take. Is this clear? The first algorithm is extremely simple. Now, the truth is that the gains are not that tremendous, okay? Like you see, it's the red curve over the green curve. However, the reason we presented it is because it's the analogous of Thompson sampling for sequential setup, which I think is interesting. Is that clear? So do you see how, so we use exactly the same DQN method that we learned earlier in our lectures. Instead of having one Q function, we have ensemble. And each time when we want to deploy our network collected trajectory, we sample one model of that ensemble and we follow the same guy for the whole trajectory. Okay? Yes.
So in these ensembles, the idea is that they know different areas of the data distribution. Do we do anything with the data that we feed them to ensure that they're very different rather than completely?
Yeah, so great question. Now here is the problem. No, this is not the case. The idea with ensembles is that from the parts of the state space where we have a lot of data, they all know that. They all will give you similar Q functions for SCOM alpha that comes from the training data. Okay. Now, when you are far away from the training data, each one will give you different Q. One will give you 10 for the same SCOM alpha. The other will give you -3 and so on. Do you see? So it's not like they're experts. It's not like a mixture of experts. It's like that you want to capture your uncertainty. Do you see? Yeah. Yes.
How does this achieve exploration if it's already learned one good path to take? Do we still have to do some kind of random starting or something such that the agent where it's an interactive environment doesn't just go, okay, this is the one way I know how to solve this. I'm keep repeating this over.
I mean, there is no such thing as there's one way. Right here, we have a Q function that tells you for specific state and actions if it's good or bad. That's all that happens here, right? So does this make sense? Yeah. So no, I don't think there is no added noise that you need to do. Okay. It's just that when you take the argmax, different Q functions will give you different argmaxes. That's all. All right. So only when you've seen a lot of data, all the argmaxes for all the Qs will be the same. Everybody will say, yes, in that state, this is the best action. Now, for states that you haven't seen a lot, each Q will give you a different action to try, and that's how exploration is achieved. Does this make sense? But on the parts of the state space where you've seen a lot, then all of them converge. Now, as you see, the games are extremely moderate, how to say, not that, so this is a very, very naive way to try to capture your uncertainty, right? Okay, so we'll see now more intelligent ways. But yes, no added thing. You just ask different Qs of what is my argmax in a particular state. Yes.
The reward graph of Frostbite looks fairly atypical compared to like the other games. Is that like an attribute of the Frostbite, or is that something that the bootstrap VPN is susceptible to, like the sudden drop of the reward?
Oh, why it goes up and down, you mean?
Is that like something that bootstrap VPN is susceptible to, or is that like...
Very good. Yes. So let me tell you, all those methods that we'll see, the non-parametric ones, the parametric ones, they have this collapse behavior because here is what happens. The curiosity and uncertainty is non-stationary, right? Something that now you are now uncertain, then you become certain. But as you become certain and you start exploring different parts, then again you become uncertain about the first thing. Do you see? So you'll see that now in the next bullet, which is great, which is a very, very important issue to see how brittle are these ways to capture curiosity. And in fact, when we go to the Go Explore paper, we'll show exactly this problem and why actually modeling curiosity in this way has not brought so far any, let's say, breakthrough. Okay. Great question. Okay, let's move on then. So that was our first approach. Let's use an ensemble of Q functions and take argmaxes from different models of the ensemble. Now we'll do what we said about modeling, let's say, surprise from transitions. So here's what we're going to do. We're going to train a policy, an actor critic, A3C, but the reward, we're going to change the rewards of the environment. The extrinsic was exactly the old reward that we all know about. It comes from the game and it comes from our environment, but we will add what we'll call the intrinsic reward, okay? And now we'll train a policy, our favorite model-free policy, in this particular next paper is going to be A3C, under this changed reward structure. So basically, I mean, the first surprising thing here, that it mathematically looks so beautiful, right? We don't need to change anything about our model-free methods to do intelligent exploration. We just need to change the reward structure to add this intrinsic reward. The interesting thing about this intrinsic reward is that it has a superscript T because it depends on the time step. It's not like extrinsic reward that is stationary. What is now new and novel, later is going to be old and boring, okay? What you're excited about on Monday, you're not excited about on Wednesday. All right? Does this make sense? So is that clear so far? Great. So now everybody will be asking, what shall we put in that math call beta T? Okay, how we will model that exploration bonus? Okay, so I'll tell you how. We'll come up with some formulations. This is the exploration bonus, have nothing to do with the task. They are task irrelevant, okay? They're just to incentivize exploration, okay? Yes, we said exactly this. So the first way to capture these exploration rewards is through state counting. We'll do the following thing. We'll train an autoencoder of the images that we see of the states, and we'll represent, every state with some small dimensional vector. We've seen this a lot when we talked about latent dynamic models. And then we will be in that latent vector. Okay, so we'll use hashing. And each time where we visit a state, we will encode it, get its code, send it to our hash table, and see how many, neighbors, how many, other states are shared in that bin. And the more the other states are, the lower the exploration bonus. All right? And so this phi s is essentially the number of neighbors in your bin from state S. And that's how you'll define your exploration bonus. Now, the incredible thing for you to realize, guys, is the following. You are supposed to try to train a policy, right? You're moving around. Once you see a state, let's say you open and you see the garden in the museum. You're like, okay, this garden is new. I haven't seen this before. I'm going to jump to a bin that has very few neighbors. Okay, so I'll give you a high reward. This is not a very easy signal for the policy to learn, right? So this means, so what's so special that I did that I was able to see the garden? Well, it's going to start doing again the garden now. It's going to be seeing more garden and so on. At some point, he's going to get bored of the garden. Okay, so then the exploration bonus is going to start going down again. It's the way, you know, this formulation here that we keep the same reward structure and we train our model free learner, and we actually reward it once it, you know, takes us to something exciting that we haven't seen before, is not that easy. For example, if I give you this task, I'll send you to a new place, a new museum, and I'll reward you each time you see something new. Okay, this is not a very easy function to define in a parametric way. I'm not sure if this makes sense. Do you see how you need to act in this particular museum is not the same as how you're going to act in a different environment. Do you see what I'm saying? Novelty is very much environment driven in this case. But this method and the next ones we're going to see do exactly that. They reward the agent for the transition that land them in this surprising state. Okay? You wanted to ask a question?
We are doing an autoencoder on the pixel data. Is that obviously we want to do like rewards because we want it to be separate.
Yeah, so I mean, that's a separate downside of that method. That look, you find a latent representation that depends on image reconstruction. And we already know that just image reconstruction cannot give you awesome latent embeddings, because a big chunk of the image may be the blue sky or the clouds that are irrelevant to the gun or the monster that actually depends on your task. Okay, but now we know how to do that better. So if you want to add the same thing, you would go, let's say, to Dreamer or whatever, Dreamer v1, Dreamer v2, where they predict us relevant quantities along with reconstructing images, and you would bin that latent embedding, correct?
Okay.
And then you would add this extra reward if you want. Okay. Yes.
Is the hash function here strongly coupled with like the environment? Because then you have to say that these particular states are similar. You should give less reward to exploration in these states. How do you formulate the hash function?
The hash function is just essentially based on the L2 distance of the latent features, right? That's the awesomeness of encoding. You just encode and you look at the embedding distances. Now, you are correct that there is a very threshold here. Either we're the same and we're the same bin, or we're different and we're in different bins. So there is a very binary idea of similarity. Yes? Same question. Yeah, so basically in that way, you are not environment dependent in the sense that, you know, your autoencoder will learn that latent space, and then you just do binning based on that L2, that embedding feature. Okay. Is that clear? Yes.
It seems like this could do really well if it was with a model-based method and not just a model-free. So really explore the space and sort of learn what's everywhere instead of having to sort of change its policy and reward function, like whenever it finds a new area that it hasn't been to before, and then eventually burning it out and then going to another one.
Great. So excellent point. So since you brought it up, we'll visit one paper like this. It's called Plan to Explore. So you train a dreamer model, essentially like a model-based method, so that you land in a state where you are really, surprised. So it's exactly the formulation that we just described. I mean, it's not using this type of exploration bonus, it's using a later formulation of exploration bonus. But since you brought it up, I think it's good to look at it. Maybe we can, visit it on Wednesday. Okay. But I think what your calling is trying to say is the following. One thing is increasing curiosity. And you say, okay, I want to add some extra rewards based on the curiosity. And the other is, how do you optimize those extra rewards? You can optimize with a model-free method, or you can optimize with a model-based method, correct? Yes, so we'll see a method that optimizes exploration bonuses with a parametric model-based method on Wednesday. All right. Yeah. So this is the first thing we saw. And there are some gains over, let's say, baselines that don't use that hash table. And clearly here we say that, oh, we need to go to a latent space and hash. If we hash on pixels, of course, things are not going to look the same because the distances don't make sense on pixel space. Two very dissimilar things can have very high L2 pixel distance, and two very similar things can have small, and two very similar, semantically similar things can have very high pixel distance. So what other ways can we come up with to define those exploration bonuses? So here is one. Instead of looking at state counting, we can look at model prediction error. All right? So we're not going to be counting states. We're going to be learning a model of our environment. This is the transition function. It's a parametric model. And then each time we take a transition, state, action, next state, we will fit that transition to our model and we'll look at its error. And if the error of our model is high, our policy will be rewarded. Okay? Do you see? So it's as if, so by the way, we are going to be learning that model as well. So we have our actor now, our critic, and the model. And the only job of the model here is to supply exploration bonuses to our policy learning method. Okay? And there is nothing complicated here. You have a model, for example, you have a model and you have also your policy, exploring the environment, and, you deploy the actions, suggest actions, you apply the action in the environment, you see the transition, you feed the transition in your model. If the model has low error, you don't reward your policy because you're like, oh, I know these things, I know this transition already. Now, if somehow the policy comes up with something really surprising, meaning that your model doesn't know about it, then you will get rewarded, and in this way you incentivize the policy to do similar transitions in the future. Okay? Questions here? We're going to see this in a bit more detail. So TS, alpha is the dynamic start transition function, essentially. There's no reward prediction here. I mean, you can also add the reward, but here is just predicting the next state, essentially. And here is Jürgen Schmidt-Huber that says the following thing so he proposed similar ideas early in 90s, okay? So he said that the goal of curiosity is to learn a world model, right? That's exactly what we said also in our first slides when we saw the baby exploring the living room. So we're curious because we want to learn about the world. This is the direct goal. The indirect goal is because as a byproduct of that curiosity, you also learn good policies for goal-directed functionals. And so he says here that you don't need to come up with different reinforcement learning frameworks to model curiosity. You just stay in the same reinforcement learning framework and you add these curiosity rewards, all right? Exactly what we just said. So what is that curiosity unit? Well, it's a reward that you get once you see a mismatch between what your model thinks about the world and what the actual world is. Exactly what we wrote. And you get a positive reinforcement if the system fails to predict the future. So you like when you are surprised, okay? Does this make sense? So that's it. So overall, we don't need to do anything else other than just add, this model, learning exactly what we saw in previous weeks. That's why we visit this deep exploration lecture today, because a big chunk of methods that use exploration rely on such model building, and then we'll use the errors of the model as our curiosity bonus. Does this make sense? Okay, and the hope is that by adding those extra curiosity bonuses, you'll be able to learn to maximize the extrinsic reward faster with less interactions with the environment. Is that clear? That's our goal. That's how we see if our curiosity-driven learning works. Did I manage to learn goal condition policies, reward maximizing policies more effectively than if I do not use these exploration bonuses? Does this all make sense so far, guys? Okay. Now, here is now the problem. The problem is, how do we learn that dynamics model, which is in a latent space? Okay, so that we're able to use it right here. And the same ideas that we saw in our model-based reinforcement learning lectures pop up here. What type of model shall we be using? Should we be predicting pixels? Should we stay in the latent space? We already have the answers now. We should be staying in the latent space, and we need to be using additional objectives to make sure that, of course, the problem does not collapse, because if you don't use any problem, all the images can be mapped to the zero vector, and so that our latent space captures task-relevant quantities. So here is the problem. Your colleague here had pointed out that this, if you just formulate your problem in this way, there is the trivial solution. So we have our current state, which is a sequence of frames. And you encode this, you jump in a latent space, you have your action. It's also encoded as an embedding. You feed them into your dynamics, what you see there as gray, and you try to predict the latent vector of the next frame. And your loss is how well you're able to predict the encoding of the next frame. But if you don't ground these encodings to anything, predicting rewards, decoding back the image observations, predicting actions or values, and so on, there is nothing that prevents that formulation of mapping all images to the zero vector. Is that clear? I mean, this is obvious. The simplest thing you can do to not to suffer from this problem is to be predicting observations back, right? So you ground those latent embeddings by adding a decoder and asking them to predict back the image. So basically, you have an autoencoder, takes the image, goes to latent space, decodes back the image pixel, so you have the reconstruction loss, and at the same time, you have the dynamics loss, that latent embedding and action better predict the latent embedding of the next frame, okay? And then you have these two losses. One says, I want to find latent embeddings that are predictable, and the other says, I want to find latent embeddings that can reconstruct my image observations, okay? And these two compete. Now, we all know what is the problem with image reconstruction, that it focuses on things that are not relevant for the task. Here is now in the next slide, a very smart little thing that this paper proposed, because this paper actually came earlier than Dreamer and so on, of how to make those latent embeddings grounded on the task to be able to use it for dynamics prediction. So here is how we're going to do it. Instead of just learning a forward dynamics model, state and action, what's the next state? We're also going to be learning an inverse dynamics model. What is an inverse dynamics model? An inverse dynamics model is the model that you get the current state and the future state, and the job of that model is to predict the action that generated the transition. Okay? So we'll take the optimization that we saw in our first slide, that we said that this has the trivial solution, and now ask those latent embeddings of the two frames to be able to decode the action. So clearly now we cannot collapse, right? Because if all frames go to zero, how they'll be able to predict the actions? Now, at the same time, if the actions of the agent really have nothing to do with the clouds, then the clouds will be discarded from our latent embedding. Is that clear that they're going to be discarded? Because they're not useful to predict those actions in the first place. Yes?
What if an action has a change that will only occur like a few times in the picture?
For example, well, in Atari, this usually doesn't happen. All this has been tried in Atari games. For example, let me tell you, here is my current state, and I'm Mario, and I decide to go left. So you'll see the next image. You'll take the original image and the next, and you say, what happened here? Oh, Mario went to the left. Mario shoot. Mario jumped. Mario went up. You just need to decode those 12 discrete choices.
But it's like Mario shoots or something, and then like a few time steps later, someone falls or something.
I see. So I shoot, and it's such a gun that you don't hear it and you don't see it. And then after a few seconds, the monster dies, right? Yeah. So let me tell you, in that case, you should not be taking the state and the immediate next state. You can just take a little bit further and try to decode the sequence of actions. By the way, people also do that. They take a state and they don't take the immediate state. So you need to predict only one action. they take few states and they try to decode the whole action trajectory. Now, the problem with this is that the further two states are, the more multimodal is the problem. There are multiple ways actions can link to states. Do you see? Maybe I'll go slow and then I run, or maybe I run and then I go slow, or maybe I just walk in normal speed. And these all trajectories, they have the same initial and final state. So that's why we don't want to, pick the two states really far away. I think you're asking a great question, but I think in this particular environment, the results of actions are immediately visible, let's say, okay? Otherwise, we would need to leave a gap. All right, a very nice little trick. Make sure that our latent embeddings don't collapse. So that's great. So they solved this problem. So now they have a model that they can use for prediction error. Now here is the other insane thing that happens to see how simple is the Atari environment. This is in the paper that you're supposed to be reading. The previous one actually is optional. They say the following: don't worry, just take a random network and freeze it. And that's fine. Then use those latent embeddings and just try to predict them. Even this is going to work in Atari games. And because you froze the encoder, clearly you cannot collapse because every frame now is mapped somewhere. This is very surprising, okay? But that's why I want you to read the paper, let alone that this is a large scale and they applied this algorithm in tons and tons and tons of environments. Okay, so let's try to put things all together now. We're going to be training actor-critic methods, A3C, with the following reward formulations. First, we're going to have only the task, the extrinsic reward, whatever. This is things that we know already. Second, we will be adding this task extrinsic reward with the intrinsic rewards, the exploration bonus. Last, we can use the extrinsic rewards that is extremely sparse, only on the last time step, plus the exploration bonus, and we'll show that this suffices because, the exploration bonus is nice and dense over time. And here is the most surprising part. We're going to throw away the task reward and we'll only use the exploration reward. I will train a policy only to surprise me and nothing else. Okay? So what do you think is going to happen if we only train for exploration rewards? Yes.
About the reward. So if you see a reward, you just explore somewhere else.
I mean, for sure, we're going to not pay any attention to the rewards. We're not going to enter in any way in our algorithm. I agree with this. But what behavior do you think that is going to emerge by, optimizing for your curiosity? Yeah.
Wouldn't it come up with a good exploration of all the space where actions have different behaviors because this was respect to actions and embeddings?
It will go to states where actions have different behaviors. Sure, yeah, and then?
And so it'll be just a really good spread of all the different behaviors of what an action could possibly do. So all the most unexpected, like how an action will, because we're doing this action prediction in this framework, correct?
No, so this action prediction, just to be clear, guys, this action prediction is only used to train your model, okay? Just because your model otherwise is going to collapse, so you're just training a dynamics model to predict, given a state and action, the embedding of the next state, and from that latent embedding, the action can be decoded. This is kind of orthogonal to your curiosity. In fact, the last version we saw is throw away the action predictions. You don't care, just freeze the encoder, start with a random network and just try to predict those latent embeddings and still try to build the dynamics model. So our goal here is we have a dynamics model and we train an A3C and we reward that A3C agent when it causes that model to fail. That's it, right? Did you want to say something?
I guess it depends on the environment, but if you have like a platform or like Mario where like you need to behave properly in order to keep going, if one experience wants to keep exploring, you can actually like at least decent with the game so that it can proceed through it.
Right. Because if you get stuck, you're going to get super bored, right? You'll be bored. You're going to die. And it's like, oh, I died. That's great. Oh, I die again. Oh, I got tired of dying. Now I need to start moving. All right. So at some point, so let's see how Mario is going to look. I mean, it's exactly what your colleague said. It looks kind of decent because it doesn't want to get stuck. Okay, it doesn't want to get stuck. Now, at some point, things are going to collapse, and you're going to start forgetting the. Again, after some time, because your model naturally will use catastrophic forgetting, will forget about how boring it is to die. Then dying is going to become exciting again. So at some point the policy will collapse. Now, clearly, I'm not showing you the collapse policy here. Okay. Well, okay, he got stuck now. Now here is something. If you take that policy and you put it on this dark environment, what do you think is going to happen? Yes?
I think it will do well because that's not really going to be relevant for our embedding the background color.
Great. So who thinks that changing the background color will actually affect our embedding? Because our policy, will take a bunch of frames, will feed an encoding, and that's how it predicts actions and Q values, right? So now my question would be, if we take that policy and we dump it to Mario by night, how is it going to perform? Like, forget about exploration. You just take a trained policy and I dump it, and I want to see how well it generalizes. What do you guys think? You can raise your hand and say something. Yes.
If it's trying to get the model to fail, the model always fails, then it doesn't matter what the agent does, right?
Great. So now your calling is asking, will we start training it again with exploration bonuses, or we'll just deploy the policy? And now for now, I'm telling you, imagine you have a policy, you trained on Mario by daylight. Okay, we trained with exploration rewards here, that's fine. Now, if you just take that policy and apply it by night without training with exploration, just apply it, what's going to happen? Yes.
It will generalize less well than this would generalize to like level 1.3 that has the same data setting.
Great. So your colleague is saying it's not going to be pathetic, but it's just not going to be as competent as the daylight Mario. Okay, right? Great. Other answers?
To make sure I understand, we're just using a random configuration of the neural network to create the embedding, or that's frozen, or how are we getting that?
Yeah. So let me tell you, I think it was not clear. Let me repeat it one more time. Whatever you see in this slide is not your policy and critic. The actor critic is something completely different. This is just to generate the rewards, the exploration bonus. You're training this transition function, okay? And then you're using here this guy. You feed the transition state, action, next state. You feed it into your model, and you look at how big is the error. And that error is what you show as reward to your algorithm, okay? So this is just a dynamics one. It has nothing to do with the policy. It has nothing to do with the critic. This is where the rewards are coming from. Is that clear?
Yeah, cool.
Great. So now we use that formulation, and we saw that somehow magically was able to train a Mario simply by curiosity, which I think is pretty cool. Now, what we're saying is not a reinforcement learning question. Now, I'm just wondering, what do you guys think about this policy? How well it's going to generalize if I change the background color? Yes.
It depends on how robust the embedding is. Like if it really discards the color, then it's the same environment.
Yes, but the question is, what do you think that this embedding is going to do? You know how it was trained. It was trained to maximize exploration rewards in daylight Mario.
So it probably discards the color because it was trained to predict, like the embedding is such that it can predict the action given to space and have only relevant features.
Okay, sure. Yes.
Since the background's always the same in daylight Mario, wouldn't it really quickly get bored of that, so it doesn't pay attention to the background? So if we switch over to the new one, it also wouldn't pay attention to the background?
Yeah, let me tell you. So when you are a policy, is not that you start switching on and off feature channels. You cannot do that. The only thing you can do as a policy is where I should go. Should I jump high or should I go to the left or should I shoot? That's all you can do as a policy. Do you see? It is not like, oh, I'm going to start switching on and off my feature channel. This is the wiring of the network. Do you see what I mean? And the wiring is the CNN. You take some images. This is a trained CNN. Is a policy is a trained CNN. Takes concatenation for frames, featureizes, averages, pools, fits it in a softmax. Here is your action distribution. And for the cricket, it is exactly the same thing with, a regression, like, a linear layer at the top. That's all. Okay. So you cannot switch on and off the wiring of your network. The only thing that network is trained to do is to produce from image embeddings actions and image embeddings Q values. That's all. Do you agree? Okay, that's it. Now the question is, those two functions that have been trained in this way to maximize rewards, predicted actions and Q values on the daylight Mario, if I put them on the nighttime Mario, what they're going to do? Do you see? You cannot say, oh, you know what? Now I decide to generalize. Let me switch on the sky. There's no such objective that incentivizes the network to forget about the sky. Do you see what I mean? Maybe in the dynamics model, something has been forgotten, okay, because it makes it more predictable. But you know what? The sky is always blue. It's super predictable. Why should I discard it? Maybe the clouds are hard to predict. So I'll discard those if they don't help me predict the actions. But green of the sky is super predictable. It doesn't cause me any problem. Do you see what I mean? And also, just to be clear here, the encoder for the dynamics model and the encoder of the policy are different networks. Is that clear? So this is super clear. Okay, now, does anybody want to say how well the daylight policy is going to generalize the nighttime? Like a couple of people said something. So your colleague said it's not going to be super pathetic. I think your other colleague said, okay, it's going to kind of do well because the color of the sky is not relevant. Any other ideas?
We'll do pretty poorly.
Pretty poorly. Why?
If so the network for the encoder and the network for the policy are different.
But when you say encoder, what do you mean? The dynamics model? Okay, let's call it the encoder of the dynamics one, the encoder of the policy, because both cases, whenever we got something big to something small, we call it encoding. So in both cases, there's an encoder, right?
Yeah.
Yeah.
And they're separate. So the policy is working originally from pixels, or is it coming from the
No, here is A3C, separately trained from pixels. Absolutely, yes.
Then because the pixels are going to be pretty different, there may not
do
be mappings that
it has learned before. Okay, so here your colleague says going to do pretty poorly. Other ideas? So basically, you switch off the light, nothing works. That's what he's saying. Other ideas? Okay, so the answer is he's going to do pretty poorly. Okay, strong. So, okay, it's just jumping up and down. That's what it's doing. Now it's going to be eaten. Okay, so this is very, very important, guys. To realize if you don't realize, let's say the limitations of the policy networks that you're training, then you will never be able to implement something useful. You need to really realize that policy has been trained on light green pixels using convolutional encoders. That's all it understands. Does this make sense? You switch off the light, oh, things look super different. I don't know what to do. Now, of course, we're going to have a lecture on augmentations using pre-trained visual encoders to help that problem. That's going to be a very fun and very easy lecture. So we will see that. But right now that we don't have such a thing, yeah, it's super pathetic if you switch off the lights. However, we can do exactly what your colleague said up there that says, who cares? This is a self-supervised method. I don't even need task rewards. I'm just going to start switching on my exploration bonuses, which means I will do it. I don't need anyone to help me. I'll start training a dynamics model, start predicting my actions or freeze my encoder, make sure I don't collapse, and use its transitions to fine-tune my agent. And you know what? It's actually going to do well. Let's see. Here, it's moving now. Let's see. After fine-tuning, it's moving. I mean, naturally, it's going to move because it was also doing well on the daylight. Is that clear? Yes.
Why not borrow the encoder of the
Dynamics model
for the
and share them. Okay, but still, you can do that. Let me think. In fact, you can do that. That's what we said that is a good idea to do. But I want to tell you, still, you're going to do pathetic because the green pixels is what is there in your encodings. And if all the green becomes black, then the network is going to predict crazy things. Do you see what I mean? All the activations, all the weights are going to overshoot. They're going to be in very, very different levels than whatever it was trained on. So that's a great idea. I think we should do it. And actually, yeah, I'm going to add some more works. I mean, I don't know if it's going to be Wednesday or Monday or it's going to be something more advanced type of lecture. But yes, we can do it, but it's not going to help us here tremendously. Okay. Yeah. One thing that could help us, and as I said, we're going to have a separate lecture, is augmentations. Oh, let me change the darkness. Let me start adding random colors. Let me start cropping, doing this and that in the environment and train on the gazillion variations of, that Mario. And hopefully that black thing will be one of the variations that you artificially generated. And then your policy is going to generalize, let's say. Okay, great. Now here is my question for you. When would that method fail? Which method? The method of training a policy to maximize, to make your prediction, your model to fail, to maximize failures of your dynamics model. When will you really get stuck? I mean, there is one thing that you're going to make progress and then collapsing. I understand that, because then dying is going to start getting exciting. And then again, you're going to get bored of dying, and then we're going to make progress, and then again, and so on. So that's one thing. But is there something that you can think that really there is something that, let's say, the agent will really get stuck because we'll find some set of actions that really make this dynamics model fail, but they don't make any progress? Yes.
Action, or you take an action and then it has like 25% probability to do different things.
Very nice. Really, really, really stochastic environments. I think this is what you're saying, right? Where we really, really cannot predict what's going on. And indeed, here is the agent is making progress in the maze, and then you give it the telecontroller, and it's just stuck there forever because the TV is all the time surprising. Okay, it's all the time surprising. You okay? Yeah, it happens to babies too. That's right. All right, and they don't even need to touch the controller because they just stay watching it. They are all the time surprised. Absolutely, absolute paralysis in front of the TV. Okay, great. So that's it. This is curiosity. Now, just to be clear here, guys, none of those curiosity versions really did something amazing that we couldn't do without having the exploration bonuses. We present them here for curiosity purposes. I think this is interesting result. Okay, so now we're going to see some alternative methods of modeling curiosity in a more parametric way through reachability and through non-parametric models. Okay, let's see. So in the higher level, the idea is the same. I learn a world model and I want to make my model to fail. Okay, it's the same idea. It's just the implementation of that model is going to be different. It's not going to be a dynamics parametric function. It's going to be a non-parametric graph. So let's see. We're going to visit two works in that domain, and they're both extremely exciting and very, very simple. The first one is super simple. Let's see. So here is an interesting paper to read, I think. It's called Episodic Curiosity Through Reachability. And basically, they have the same formulation as what we've seen. We're going to be training an agent with a model-free RL. We'll see model-based since because your colleague brought it up. I thought that was a very interesting comment. But again, we're going to be using model-free reinforcement learning, and we're going to be coupling our extrinsic rewards with our exploration rewards. But this time, our dynamics model will be non-parametric as opposed to parametric. That's it. We're not going to have a transition function like the previous paper. We're going to have some graph representation of our environment. And we'll see exactly how we're going to do that. And we're going to be using PPO. That's going to be our favorite model-free method, not A3C, PPO. I mean, that's it. Questions? Yes. In the TV.
the TV images are not really helping you predict what action you took, right? Like if you went there and you took left or right or whatever. On the next page, as you're observing TV, the images are not really helping you predict the action. So
Yeah.
shouldn't it be discarded by the latent encoding of the image?
Yeah. So, okay, let's try to think what you're saying. So, number one, I'm not sure if they're using there the frozen encoder or the other. Okay. So, if it's the frozen encoder, the frozen weights, clearly every image will have a different embedding vector. Okay. And so this for sure is going to fail. Do you agree? Because you won't be able to predict it. So always you'll have high prediction error. Do you agree? Okay. Now, what you're saying in the other case, where given what we saw, we need to be predicting which channel we picked. All right. And what you're saying, yeah.
Oh.
What?
Oh, I didn't know we were also like picking channels. I just saw it was a moment. If you're picking channels, then it will influence that.
Yes. Oh, you're saying either you can switch the TV or take another action in the corridor. You thought that this is just one action that was changing the TV all the time?
I just thought we were moving in the maze. Like I didn't realize we were also picking an action in the remote.
Okay, if we don't pick an action from the remote, what is the problem? That this new state embedding cannot tell you what action you took?
So it should be good.
And eventually would be predictable, right? Well, let me tell you, there is one way to get around this problem. And this is the following thing. This is very weird, but it's the following. Instead of having one dynamics model, you have ensembles. Okay, now let me tell you why you have ensembles here. It's pretty crazy. Because and the way you measure surprise is from the entropy of your ensemble. What does this mean? This means in the beginning, all those three models of the ensemble will try to predict what the TV is going to show. And they're all going to saying different things. Okay? So then you're going to have high entropy. And high entropy is high surprise. So you like it a lot. So you keep watching the TV. Now, at some point, all models of the ensemble will be predicting the average next frame because that's what L2 does. You train each model of the ensemble is trained with L2, right? Is it just a standard deterministic regression network? So they're all going to, default to the mean next frame. And once they all default and fail, basically, once all of them fail, then they're going to fail in the same way. And then their entropy is going to be low. And then you're going to say, okay, I'm not excited anymore. Let me just move on. Okay. Does this make sense? Okay. I'm not sure if this is now, to be honest, the way I think about it, because I think your question is good. Like, why then it becomes predictable in the first place? Because it went to the average next frame.
No, I'm not following.
That's okay. So don't worry. I will look into this question. I think your question is the following. Why we cannot predict the average embedding of the next channels, let's say, that you see? So let me look into this and I'll get back to you. Okay. And why having an ensemble of those dynamics models is more helpful than just having one and looking at its default. Okay. Yeah.
Each frame is going to be different from the average next frame. So wouldn't it sort of always be rewarding?
Oh, yes, exactly. Perfect. So your colleague answered the question. So he says, indeed, you can be predicting the average. So you're going to be failing. But once you fail, you're still going to have huge prediction error because you're predicting the average, which is probably some gray image. Now that gray image is going to be very different than all the different images that the TV shows. So you'll always have high prediction error. However, once you put ensembles and they all predict gray images, their entropy is going to be low. Okay. And so then you can just stop being surprised. Okay, great. Is that clear?
So my question was more about the learned encoding.
Yes.
Whether it's going to discard the different channels.
Even if it's going to discard it, still is not going to be able to predict the next well, I feel. Do you see what I mean? Because the next image is always going to be something really crazy, and that's going to be the output of your encoder. Right? Basically, this won't be able to work anymore because you won't be able to predict that action. You're going to have very high loss. Do you see? So that auxiliary task that you added, oh, I want to be able to decode the action from dilate and embedding, will have very high loss. You will never be able to predict your action. Okay? No matter what you do, even if you discard whatever you want to discard, it's not going to improve the action predictability. Is that clear? Okay, great. Thank you for intervening. That was great.
And I have one more question.
Okay, sure.
So with the TV problem, has anyone tried sort of doing second order surprise, sort of like, if it's more surprising than you expected, then you want to learn about it, but after a while, you know that the TV is just has stuff you can't predict. And
yeah, okay. But how do you know that his stuff you can predict? You didn't like the ensemble solution. That was one way. It's called, there is a recent ICML paper by the same authors. It's called exploration through disagreement. So you look at your ensembles. When they disagree, you get excited. When they agree, you get bored. Do you see? So that solves the TV problem. All right? Because at the end, all models of the ensemble will predict gray, because none of them will be able to predict the future, so they will default on the mean prediction. Is that clear? So that's one way to get over the TV problem. Is that clear, guys, to everybody? This tiny change that we did, I mean, we can also visit the paper, but this is the main idea. Everything stays the same, but instead of looking at your prediction error, you have multiple models of the dynamics models, and you look at their entropy, and the entropy goes into your exploration bonus. High entropy is high exploration bonus, low entropy, low exploration bonus. Okay? Okay. Now, and the idea is that even for crazy worlds like TV, still all the models will agree. Will agree on something wrong, something unpredictable. They didn't agree on being able to predict the future, but they agreed on failing to predict the future. Okay? I decided that I cannot predict it because, look, we all agree, we all have high prediction error, but we are in agreement about that. Do you see? Very interesting with this ensemble. Any questions here? Yes.
What happens if there's like something in your environment that's weird in a way that all the networks think, oh yeah, this is obviously what should happen here, but something different happens. So they agree about what should happen, but that doesn't match the reality. Do you still get surprised in that ensemble method because they all agree on the wrong thing?
Yes, that's exactly what happened here. Okay, that's exactly what happened. They all agree that what's going to happen if you press the TV is going to be some gray image. This is not correct, but because they all agreed, you are not going to get surprised.
Does that negatively impact exploration on like non-TV situations where like you're going down a hallway and you don't expect a door, but all of a sudden there is a door?
No, no, this does not. This does not. Does anybody want to answer to your colleague why this situation does not impact? Well, because in that case, let's say I open the door and I see some pink cake in the middle of the table. Well, I got surprised here. You also got surprised and he also got surprised. We got surprised in different ways. Our entropy is high. I was expecting something, you was expecting something else. Do you see?
What if like there'd been 100 rooms before and every time you opened it, they had a blue cake and this time it's a pink cake. So everybody predicted a blue cake, but now it's a pink cake. So you all made the same.
We all got fooled.
Yeah, in the same way. What's this?
Okay, well, these environments are not so fancy, but yeah, but in that way that you pose it, yeah, this is not like, oh yeah, you've seen this same door before, but now it's a very weird octopus that enters. No, it doesn't. It didn't happen. It didn't happen. But let's see. Yes. Yes, this would not be able. This formulation wouldn't be able to handle this the way you pose it. Okay. But let's see about non-parametric formulations. Let's see maybe how they can handle or not. Okay. Very simple things here, guys. So here is the memory. Has a bunch of nodes. What are the nodes? The nodes are just images I've seen, states I've been. Okay, encodings of images essentially. That's what it is. And what are the edges? The edges, guys, are how close two nodes are. So not only we need to have a set of nodes, we need to have a graph. We need to reason about transitioning from one node to the next. Now, how we are going to estimate those distances between nodes? In extremely naive way. Yes, by the way, the memory here is this green, sorry, is this blue thing. This is my memory. These are my observations. Now, other observations are going to come, and I need to be able to reason, are these close to things I've seen, or they are really far away? If they're close to things I've seen, I'm not surprised. If they're far away, I'm surprised. Okay, that's what it is. So let's see. First of all, the obvious thing is, how do we estimate those distances? So here is how. We're going to have trajectories in the environment. Trajectory is a sequence of states and actions, exactly what you see here. Okay. Anchored on this observation, you will have some positive ones, observations that are nearby in time, and some negative ones. Now you may say, what's going to happen if I do a circle? And then, at the last I land the same as in the beginning? Well, you're going to make a mistake on your labelings here. Here assumes that the further in time, the more dissimilar things are. Okay, this is the idea. So you're going to use this type of self-generated labels. So this is a pretext task. You came up with a task to decide which frames are close and which frames are far using your trajectories. And you're going to train this comparator network. What is a comparator network? It's a Siamese network that takes two images, featureizes both of them in the same way, and then looks at those features jointly and decides whether they're close or far. Okay? And you will train in this contrastive way. So you'll have one observation O, a positive observation O plus sampled from here, and the negative observation O minus sampled from further away in time. And you will train the encoding weights, okay, so that the encoding, the O and the positive pair in embedding distance are close. So this L2 is minimized. And the distance between the observation and the negative are larger than the margin gamma. If they're larger than that margin, you don't push any gradients, you're happy. If they're not, if they're smaller than gamma, then you need to, there is a gradient coming from this term that updates the weights phi. Is that clear? Yes.
What benefit does the margin have over just the negatives of that distance?
Because you don't care to be pushing those guys forever far away. If they're beyond the margin, you're good. You don't need to squeeze your network to put them forever apart. Does this make sense?
That's another way of regularizing it so that they don't generate like arbitrarily high.
Yes. Also because otherwise all these phi weights are going to be occupied pushing far away things, which you don't care about. If they're far away beyond some time, they're far. That's fine. Okay. Does this make sense? So you will see this margin in all those, let's say, ranking formulations, where there is one observation, a positive and a negative. You put the observation and the positive close, you put the observation and the negative above a margin. So our goal here is to map images to embedding vectors, so that by comparing embedding vectors, by taking their products or L2 distances on that embedding space, we can essentially read off the organization of those images. Okay? So if I have two images, I pass them in the coding, I see their embedding distance, I can say, oh yeah, these are very close. Or no, these are far. Okay, this is our goal. This is called metric learning. We want to learn a metric. We want to train the weights phi so that the metrics between my images make sense based on this temporal contrastive task that I came up with. Now, once I train the comparative network in this way, what have I achieved? Well, here's what you'll have to achieve. You move around, you're an agent and you move around, and each time step, you see an image. And then you push it through your encoder, and you get the embedding of that image or this observation. Then you'll compare it with everything you have in your memory. Okay? And if the distance to things that you have in your memory are small, then you're like, oh, I'm not going to put any reward to myself. I've been here before. But if it's high, you do two things. First of all, you get rewarded. And second of all, you expand your memory. You're like, oh, by the way, I've been there before now. You go to the museum, you see this awesome room with a mummy, okay? Then you put that image in your memory. So next time, when you see similar mummy image, you know that you're not surprised. Is that clear? Now, there is some huge difference here, guys, between parametric and non-parametric ways of reasoning about dynamics. Here is how. In the parametric case, when we're training a function to predict state and action next state, if you see a transition, okay, let's say you happen and you see that pink cake, your model, yeah, once you see that pink cake, next time you see it again, you open the door, you see the pink cake, you get surprised, high prediction error. Then you throw this data in your model, so you keep training your model. Next time you open the door and you see the pink cake, again, you're going to be surprised. Then you say, oh, pink cake. You throw it again in your training data. You keep training your dynamics model. Next time you open the door, oh, a pink cake, surprised, and so on. Why? Because a parametric function, to be able to learn something, requires multiple gradient descents. Do you see? It cannot learn instantaneously. It cannot do fast learning. That's why I say it calls slow learning and fast learning. Fast learning is with non-parametric structures. Slow learning is through gradients on weights of the networks. Is that clear? So basically my point is that for your dynamics model to stop being surprised about something, you really need to collect a lot of observations, throw it into its repository and keep training. By the way, I'm not sure if it was clear, but this dynamics model is concurrently trained with a policy, right? When we saw the Mario, you remember? So as you train your policy with more observation, you also train your dynamics model. So what is surprising and not is changing over time. Is that clear? Was that clear there or no? I'm not sure if we made it clear. So that's very important, okay? So both of things are you keep training, both the policy and the dynamics. And here, the good thing with this non-parametric memory structure is once you see the pink cake and you add in your memory, next time you're not surprised. So this is fast learning because your memory repository changed and now you compare against this additional item. Do you have any questions on this? Yes.
So is the comparator also being trained currently as the wouldn't it by definition be less reliable for the states that are smarter and not in your memory if you haven't seen them yet?
I think the question was whether this comparative network is also jointly trained as the data comes, right? Yes, the answer is yes.
So like if you saw a pink cake, would you have a guarantee that it's going to be far away from everything or because you've never seen that before?
Yes, you will have a guarantee because usually, even if you train a, frozen network and you fire it on a pink cake, the feature vector is going to look very different than without the pink cake. Okay. Does this make sense? So my point is this metric learning, even if you train a pre-trained network, let's say on ImageNet or Rigo4D with some self-supervised objective, already is going to give you very reasonable distances. Now you can fine tune to your trajectories. This is great. That's fine. But do you see what I mean? But even if you take something pre-trained, we'll be able to tell you something useful. Okay. While in the previous case, in the parametric case, when we're predicting the next state, you cannot take anything ready. You need to train or from scratch something for your domain. Okay. Mm-hmm. I'm not saying it's going to be perfect, but I'm just saying it's going to be irrelevant. Like for sure, the pink cake for sure is going to be like novel. All right. Questions here? This is a very important idea here with this non-parametric memory. So I have one more picture. Here is the current observation. We encode it. And this is a memory buffer. Here is everything I've seen in my memory. These are also encoded with the encoding network. Now we're comparing and we see, is there any state in my memory from which this new observation is reachable? If no, then I get a reward bonus and I add this observation in memory. If yes, I don't get a reward bonus and I don't add that image in memory. All right. Okay. And because the encoder changes over time, you may need to be re-encoding these memory images. Okay. So what do you see here, guys, on the results? You see that it's doing much, much faster. It learns much, much faster than PPO. PPO is sitting down here dying. And here is ICM, which is intrinsic curiosity. This is the paper we saw earlier with a parametric dynamics model. This is this blue. And you see that the non-parametric dynamics model learns faster. Okay? Questions? Very simple. Isn't this super simple? By the way, so far we have A3C and PPO running, right? Exactly like we learned it from the first lectures, plus an additional module training a parametric model, plus training a non-parametric memory with a comparative network and computing distances, right? We just add an extra module, and that extra module supplies an exploration bonus to our model-free learner. Is this clear? Okay, do you have any questions? Okay. I'm wondering if I can ask a question here, but all right. Anyhow, that's fine. So we have a model. Now we have this weird disconnect that we have an awesome model, parametric or non-parametric, and somehow we use model-free methods to optimize the exploration reward as opposed to having also model-based method to move around. But that's another story. So now we're going to go to a very interesting, in my opinion, paper that does use any neural network. There is zero neural network. We're going to solve Montezuma's revenge from the beginning to the end without using any GPUs, okay? And we have only 3 minutes, but in these 3 minutes, we will discuss how the curiosity formulations we have presented so far can fail, which is very, very important. Intrinsic motivation, it helps by why it hasn't worked better so far. But by the way, the motivation for this paper is similar to the motivation of the previous paper, okay? It's just that along with this huge non-parametric memory, they build on top of that a different solution method. So I find this way more, let's say, forward-looking or groundbreaking. Now, here is what happens. Imagine that you are a curiosity agent and you start here in this environment. And you're like, you know what? What if I start exploring to the left? And you explore and everything is nice and interesting, etc. And you made some progress. And then at some point, you die and you need to go back here. All right? Now, you go back here, but by looking to the left, everything here looks very predictable because you know about those things. All right? So you're not going to choose to go to the left. You're going to choose to go to the right. So you explore, and then at some point you die, so you start here. So now what happens? You are not incentivized to look to the left. You left a big chunk of your environment unexplored. What prevents you? There is this part of the environment coming immediate next to you, which is actually boring. So the policy will not be getting reward to cross that part. Okay, now you may say, sure, but if we wait long enough, then it will get exciting again, which is true. And once you get exciting again, you're going to go to the left and you're going to be playing. But then again, at some point, you know, as you're dying and start from the beginning, your incentive of going to the left is going to be going lower and lower and lower. Do you see the problem? So what do we mean by this? There is no methodic exploration of your environment. There is no methodic exploration of your environment. There is no external memory or where you have been and where you haven't been. What these people are suggesting is that we need external memory repositories. That's what they're saying. Okay? Much like the previous paper. Why? Because in external memory repositories, you can actually remember where you died. Okay? For example, you were seeing some super awesome new stuff in the museum. Then your mom said, oh, let's go have lunch. You have lunch, but then you don't forget where you were. You don't forget where you were. You were in this particular location watching this awesome painting. So you'll go there and start from there. As opposed to like, oh, I need to be excited now. Do you see what I mean? To get incentivized to move around, which is so logical. It makes so much sense, okay, to have external memories to model the environment as well as to guide our exploration. Do you buy that argument? Okay, well, they also support that. They call this detachment. They said that, I mean, detachment is a very not obvious term. Yeah, and they say, you know, throwing experience in replay buffers is not going to help you remember better. These replay buffers are huge. Cool stuff happened once after 1 million times. You sample from that replay buffer, then clearly all the good stuff have been forgotten and so on. And they say, I want you to explicitly remember where the promising locations are, how to get back to them. And you don't want to be detached. You want, if somebody distracts you from doing progress, maybe the monster ate you, right? But next time I play I remember exactly where I failed last time. And I really look forward to get there and continue. So this is what these people propose. We'll see how they solve it next time because it's 110. But on Wednesday, we'll go back and visit this paper, and you can take a look at it at home also, so you can pre-read it. Okay. See you on Wednesday.